Hey everybody, and welcome to Art of Navaids. Today we're going to be discussing the Vector Network Analyzer, or VNA. And the particular model that I'm using today is made by Keysight. They call it the FieldFox RF Analyzer, and this is the N9913 Alpha, which goes up to 4 gigahertz. The most basic explanation of what a FieldFox is a signal generator that's capable of receiving its own signal. What we use this most often in navigational aids for is measuring the phase and amplitude relationships between various cables in the antenna arrays or feed cables from transmitters to antennas, and of course testing of antennas for VSWR or return loss. So you can see that the network analyzer, particularly the handheld FieldFox, is one of the most important pieces of test equipment in NavAids maintenance. Some things that I have here on the table are a dummy load, attenuator, an antenna, and a 90-degree phasing cable used in localizer maintenance. These are things that can all be tested on the network analyzer. For instance, the dummy load, we want to ensure that it's properly absorbing all the RF power that it's supposed to. And this is important for doing any kind of testing that requires the use of multiple dummy loads, such as testing the distribution unit of a localizer antenna array, or dummy loading the monitor port on an antenna. Another device would be an attenuator, such as this 3 dB attenuator. We'd want to measure this to make sure it actually is attenuating by 3 dB at a specific frequency. This would be important in order to make power measurements, where we need to include all attenuation in the power meter offset. And yes, you can use the FieldFox to make power measurements, which I'll get to in another video. And of course, we can also make measurements of antennas, where we can look at the VSWR, or the dB value, or also known as return loss. The dB is what we use most often in NavAids, not necessarily the VSWR ratio. And then another important thing is measuring the phase or electrical length of a cable. And I have here a 90-degree phasing cable used for localizer maintenance. And this is something that we could confirm on the FieldFox was actually 90 degrees, and if it wasn't, we'd know how much to cut to correct for that phase length. And there's numerous cables in the localizer and glide slope and in the VOR that are all phase dependent. And just for a little bit of terminology, all the devices on this table are referred to as devices under test when looking at them on the FieldFox. Now, before we begin our walkthrough, we need to take a moment to discuss some key terms that you should know. And we'll start with Vector Network Analyzer and what we mean by vector. Then we'll move to scattering parameters, VSWR versus return loss, and phase. Now, a vector is just a quantity that has a magnitude and a direction. And we can express this graphically and numerically. That's what the FieldFox RF Analyzer does, is display these vectors numerically. Now, vectors can also be represented graphically, and we use them a lot in explaining the ILS radiation principles. Here's an arrow that is possibly maybe representative of 0 dB amplitude at 0 degrees phase. And another arrow I might draw could be negative 3 dB because it's just half the power of that red one. And it has a phase of negative 90 degrees relative to that red arrow. Let's say that red arrow might be the reference. So essentially the FieldFox is just telling us the numerical values of these vectors. Now, the next term is called scattering parameters, or sometimes referred to as S parameters. And a scattering parameter is simply a way to describe the way the RF is scattered either away from a device under test or through the device under test. And it's often expressed as an S11 measurement or an S21 measurement. So for example, if we had a device under test that had 2 ports on it, this would be port 1 and this would be port 2. We would be using an S21 measurement to be looking through the device under test to see how much power was being lost or gained. Since the energy is emerging from port 2 and then entering in to port 1, it's referred to as an S21 measurement. We can also make measurements of the power being reflected back to us with an S11 measurement. And since the energy is both emerging from port 1 and entering on port 1, it's referred to as an S11 measurement. The next two terms are VSWR, sometimes pronounced VSWR, stands for voltage standing wave ratio, versus return loss. And these two terms seem to be interchangeable, but they do represent different ways of measuring an impedance mismatch. In Navigate's maintenance, we use return loss far more than we use VSWR, but you may see specifications expressed in either VSWR or return loss in technical manuals. And oftentimes you can just convert from one to the other. And what VSWR is it's the result of the signal being sent from a source being reflected off of a load, and the sum of those two signals, if there's a significant amount reflected back, results in something that looks like a standing wave. And VSWR is just the ratio of the maximum and minimum amplitude of that standing wave. On the other hand, the return loss is just the signal that's reflected back to us as a result of that impedance mismatch. And it's often expressed in the decibel, or dB. To make return loss measurements in dB, you'll always be using the S11 scattering parameter and using the log mag measurement type, or logarithmic magnitude. This will give us a measure of amplitude in dB. Now the last term here is phase, and that's why I have up here what I refer to as the vector diagram, or phase wheel. And the vector diagram here is really going to help show you visually what that vector is doing. So later in this video, I'm going to be measuring a 90-degree cable. But before we measure our device under test, we'll take a 0 reference. So they'll be reading 0 on the phase trace. Once we insert that device under test, or 90-degree cable, we'll see a new phase reading show up of around -90, indicating that this vector, or that wavelength, is now delayed. And so what this vector diagram is trying to show you is that anytime you add cable after a 0 reference, you will move around this vector diagram in a clockwise direction. And conversely, if you were to make anything shorter from the reference, like shorten your cable from the reference, you would be moving around this diagram in a counterclockwise direction. And we can compare the vector diagram to a sine wave, since a sine wave is essentially a circle. Now watch as the waveform on the left is delaying by 90 degrees. What's happening to the vector? Now in this video, we're going to be just discussing the network analyzer mode and the vector voltmeter mode. And in order to follow along, you're going to make sure that your FieldFox has options 210, 211, and 308 installed in order to do full 2-port transmission testing and reflection testing. And then of course the vector voltmeter mode is an option all into itself. Now you can verify what kind of options you have installed in one of two ways. Either you can go to the mode button and look at under the different soft keys. You can see if you've got network analyzer mode and vector voltmeter mode, or you can go to number 7, system configuration, and then select options, and then show options to get a list of the installed options on your FieldFox. Before we get started, you should know that all the buttons below here have functions that don't change. The buttons up here just below the screen are referred to as soft keys, and the functions do change depending upon what's displayed on the screen right above that button. You should note here that we've also got 2 RF cables connected to port 1 and port 2. These are RG223 cables with N-type connectors on them, and I've color-coded both ends of the cables just to eliminate any confusion. In order to demonstrate the capabilities of the FieldFox Network Analyzer, I'm going to be measuring this RF cable with an attenuator connected on the end. So I've got some electrical phase length here along with some attenuation. And right off the bat, this is going to let me know that I'm going to have to set up the FieldFox for a through type measurement, or an S21, and display both amplitude and phase. So let's begin by selecting the mode function and then the soft key for Network Analyzer, or NA, to bring up the Network Analyzer mode. And we can confirm that up here in the top left by making sure that it says NA. Now to get started, we know that we first are wanting to look at amplitude and phase, so we should bring up two traces. Right now this is just one trace showing on the screen. If we hit number 6, trace key, and then number of traces, and select 2H, this is going to put now two traces, one above the other. So let's begin formatting trace 1 for amplitude. By default, it already comes up measuring in dB, or logarithmic magnitude. So we don't need to adjust that. But we do need to change the scattering parameter from an S11 to an S21. And we can do that by selecting measure and then S21. And that changes it for trace 1, and it looks like it changed it for trace 2. Now let's change the scale for trace 1 by selecting scale. And you can see here for each division on the trace, we have 10 dB per division with a reference level of 0 dB and a reference position of 5. I'm going to change this reference position up to 0, which is going to put 0 up at the top of the trace, and that's going to bring up some of the lower level amplitudes. And now I'm showing from the top of the trace 0 dB all the way down to negative 100, which is going to give me a nice visual range of the amplitude for that trace. Now let's move down to trace 2 and format that one by selecting trace, trace 2, and you can see that it's highlighted now, meaning that's the active trace. Under measure, we can confirm that it's also set to S21, and under the format, we can change it from logarithmic magnitude, which was the default format, to phase. And you can see some of the other options that we have here, but for this discussion, we're going to keep to phase. And then back to scale. Everything is already set here with a scale of 36 degrees per division and a reference level of 0 degrees with a reference position of 5. With all of these settings in here, this gives us a nice visual range of a full 360 degrees. This is pretty much the same convention that all vector network analyzers use, positive 180 to negative 180 for 360 degrees total. And the next thing we need to set up is frequency. And you notice we've got two areas that we can change the frequency in. That's either from the start to the stop or from the center to a span. I prefer to set the center frequency first. For us, I'm going to choose 110.1 megahertz. I'm going to select a frequency span of 1 kilohertz, which is a relatively small span, which I'm not concerned with. I'm just looking at this cable and attenuator at one particular frequency, which is known as usually the station assigned frequency. When a frequency span becomes important on the network analyzer is when I'm tuning a filter that has to be a certain bandwidth, or I'm trying to tune an antenna using some impedance matchers like in the VOR. Okay, now it's time to perform calibration by hitting the number 5 calibration key. And calibration is important to perform every time we start up our FieldFox for the first time. There are well-defined and understood systematic errors that are measured and calculated during the calibration process. And so when we perform this calibration, it removes those from any subsequent measurements. You should have with you the calibration-T accessory, and the part number of mine is the 3605. On the FieldFox, when we hit mechanical calibration to bring up this process, it's already recommending that we do a full 2-port calibration based on our S21 settings. And you can see that it selected the 3607 calibration kit. And that's this, but with male N-type connectors on all the sides. So we can actually change this to match the calibration T that I have by selecting Change DUT Connectors. And then using the scroll wheel, you can select type in and then change gender. And then do that for the next port, port 2, and then next. And now it's bringing up all the calibration kits that would match that connection type. And of course, the first one here is the one I have, the 3605. So we're going to select that calibration-T for both ports and then hit finish. And now we can start the calibration. So for port 1, which is the green cable here, it calls for a short. And so you can read the sides of the calibration-T to figure out what side is what. We measure. Now it wants the open. Now it wants the load. Now we're ready for port 2. Short. And open. And load. And the last one is port 1 to port 2, and I'm going to use an N-type bullet for that. And that completes the calibration process. And now that port 1 and port 2 are connected, everything looks stable. But first we need to set up a marker. So if I hit marker and then normal, by default it's put our marker normal on the center frequency that we set from the frequency function. If we wanted to change that, we would just key in using the number key a new a new marker. And you have several markers that you can add to the traces, as well as marker delta options. And we can see with our normal marker set, on the top right of each trace, M1, 110.1 megahertz, I'm reading a very small amplitude here of 0.009, and that's pretty much 0. And we can see here that we've got negative 3.8 degrees for the phase trace. The next thing we need to do is perform a normalization or take a zero reference, and this goes hand in hand pretty much with the calibration process, where we zero out the amplitude and we zero out the phase reading before we insert any device under test. So we're going to do that by selecting trace, and then for trace 1, we do that by selecting math and memory. And we have to store the current data into the memory and then select the math operation. And it's always going to be data divided by memory that we use for navigational lathe maintenance. And then one more time, I like to just select data to memory and get that tone, and then you can see I've still got 0 up here. Let's go down here and do it to the phase trace. So select trace, trace 2, now trace 2 is highlighted. We're going to select math and memory. And notice that it still says negative 3.8, so we're going to store that data to the memory and then select the math operation of data divided by memory, and it immediately compares the new data to the old data to create a 0 reference. And if you wanted to, you could hit that one more time, that data to memory, just to ensure that it is zeroed out. The reading up here is fluctuating quite a bit, but you have to realize that it's in milli-degrees. So if I was to look at this, if I could get a reading on that, it's at 50 milli-degrees. In reality, that's a 0.05 degrees, which is pretty much 0. So now we're ready to insert the device under test. And there's nothing directional about this test cable, so it doesn't matter what port goes to which end on this setup. Now that we're connected, I'm reading a negative 2.93 dB. I usually only round to the nearest tenth, so a negative 2.9 for amplitude, and for the phase, I'm reading a negative 99.3. And I don't really usually want to see a lot of fluctuation on these readings, definitely nothing more for something like this, more than a few tenths of a degree. If you're getting a lot of fluctuations on these readings here, that's going to indicate there's something wrong with the connection or possibly a ground of the RF cable, and would be something definitely worth investigating. So that concludes making an S21 measurement on something that we want to look through. Let's look at something that would require an S11 measurement, like an antenna or a dummy load. In measuring an antenna in this room would not be ideal because I've got a lot of things around me that would affect that measurement. But a dummy load would be a good example for this exercise. Now I do want to point out that you can check a dummy load with an ohm meter because they're purely resistive. There is no inductive or capacitive qualities to them. But what I found sometimes is that when testing them with the test leads where I can touch directly the center conductor and the shield, I can get 50 ohms, where sometimes when I look at them on the network analyzer and I actually connect using the N-type adapter, there's something mechanically in the connection that's not quite good, that is not revealed when I'm using the ohm meter test leads. So for that reason, I do prefer to check these with the network analyzer. So to reiterate, when I test this dummy load, I'm only concerned with the amplitude trace on the FieldFox and how much power is being absorbed or reflected back to me. What I ideally would like to see is nothing less than negative 21 dB, and we'll look at that. It should easily pass on this test. So the first thing we're going to select is trace 1, and I need to change this over to an S11 measurement. Okay, now it's time to perform the normalization or the zero reference. And I just want to make sure that the test leads that I need, all the adapters that I need to connect to the device under test are already connected to port 1 so that they can be factored out. We do that by first going to trace 1, and then the math and memory. The data math is already still selected for data divided by memory. All we need to do is select data to memory to get a new reference. And just to verify, I look up here and I got a 0.00 and then some very low dB values. And so we're ready to go ahead and take that measurement of the dummy load. And I can see that it's a lot better than negative 21. It's actually coming in at a negative 41 dB, which is a pass for dummy loads. Now that concludes basic operation of the network analyzer mode. Let's look at the Vector Voltmeter Mode, which for the Vector Voltmeter Mode, when you select mode, you should see VVM as an option. This is option 308, so you'll have to have that installed if you want to access this feature. Now the great thing about the Vector Voltmeter Mode is it's very easy to use, but it's only designed to be used at specific frequencies. So unlike the network analyzer, you can't use this mode to sweep a range of frequencies. You're not going to be able to tune anything with this, like a filter, or maybe see the response of an antenna at a range of frequencies. It's just designed for one frequency. But it shows it very simplistically with magnitude up here and your phase down here, and you'll be amazed at how quick the setup is compared to the network analyzer. And just to demonstrate that, I'm going to test the cable and attenuator just like I did for the network analyzer mode, but on the Vector Voltmeter mode here. We're going to start by selecting under measure 2 port. So this will utilize both ports, sending from port 1, receiving on port 2. And then we're going to get hit the frequency key, and then frequency again, and we're going to set up 110. megahertz. And you can always verify that here under F equals, and then you can see the frequency there. Now we need to perform our calibration, which is the same process as the network analyzer mode. And I just hit cal, number 5, and I'll go through that process now. Okay, I just completed a full 2-port mechanical calibration, and the next step is going to be to normalize or take a 0 reference. And so if we hit measure setup, the number 4 key, we can see that the 0 is currently turned off. And so all we need to do is simply turn it on. And now I have still 0 dB. If there was anything there, that would have zeroed it out, just like you see here. And then, of course, the degrees is now zeroed. And now we can connect our device under test. And now you can see with very minimal input on the FieldFox, we were able to set this thing up and get pretty much the same results we got on the network analyzer mode, a negative 2.9 dB and a negative 99.4 degrees for this device under test. Let's go ahead and look at a reflective measurement and like an S11 measurement. And so in order to do that, we're just going to select measure, and then port 1 also says port 1 cable trimming. That's not necessarily what we're doing with it, but it's going to serve the purpose for an S11 measurement. So port 1 cable trimming is for reflective measurements, antennas and dummy loads, and port 2 is transmission, which is a little bit more obvious, and it's what we just completed. You can see I've got some numbers on here that I need to normalize and take this off, but we need to go ahead and remove the device under test that I was using, and just bring it down to the test cable and adapter that we're going to use that are going to be necessary to connect to the dummy load. So with this, I can go ahead and select measure setup and then 0 on to get 0 on amplitude and phase, and then I can connect the dummy load. And I'm not concerned with the phase of the dummy load, but rather the amplitude, and that's about what we got on the network analyzer as well, negative 40.1. So this concludes some of the basics that you need in order to operate the network analyzer or vector voltmeter mode. Hopefully you have a better understanding of the differences between the two modes and which one might be best to use for your application. Stay tuned or be on the lookout for some other videos I'm going to do on the TDR or time domain reflectometer under the CAT mode, the cable antenna test mode, and the power meter mode. And as always, thanks for watching.